Welcome to This Explainer. I'm an environmental engineer, and I've spent my entire career analyzing incredibly complex systems. But today, we are looking at the absolute holy grail of engineering, pulling drinking water straight out of the driest air on Earth. We're talking military-grade hardware, nanotechnology, and raw physics coming together to make the impossible happen. Let's jump right into it.
To really grasp why this is such a massive challenge, you have to understand the extreme physical limits we're up against. Out in the harshest deserts, a cubic meter of air holds, at best, less than 5 grams of water. That is our target. We have to engineer a way to pull a practically invisible, incredibly scarce resource out of massive volumes of moving air. Honestly, it's an environmental engineer's worst nightmare. The contrast here is just staggering. Take humid, coastal air, you're looking at 20 to 30 grams of water per cubic meter, but desert air, barely 1 to 5 grams. So if you run the exact same volume of air through a system in an arid climate, you're extracting up to 20 times less water. You absolutely cannot just take a commercial machine built for Miami, drop it in the middle of the Sahara, and expect a single drop. It doesn't work that way.
And the exact math behind why standard systems fail is right here in the dew point approximation formula. We've got T for ambient temperature and RH for relative humidity. This equation brutally highlights our biggest roadblock. As relative humidity drops toward that 10% mark in a desert, the temperature you need to actually condense water, the dew point, just plummets. You'd have to actively freeze the air down to unnatural extremes just to force a single drop of condensation. Because that dew point plummets so far, standard refrigeration-based water generators just fail completely. The extreme ambient heat forces their compressors to run 24/7, eventually pushing them to total system failure. Plus, the desert is an actively hostile environment. Abrasive, microscopic sand quickly shreds mechanical fans to pieces, and fine dust clogs up intake filters in a matter of hours. The physical wear and tear on unprotected moving parts is catastrophic. Let's break down the thermodynamics of that failure. Actively cooling desert air to hit that elusive dew point eats up a staggering amount of power, up to a full kilowatt-hour just for a single liter of water. To put that into real-world perspective, it's like running a heavy-duty washing machine for an hour just to get a sip of water. In a remote, off-grid desert setting, that kind of energy cost is completely unsustainable. We desperately need systems that operate near zero active energy.
Section 1. Military-grade engineering solutions.
So to solve these catastrophic mechanical and energy failures, we actually turn to battlefield engineering. Organizations like DARPA are completely revolutionizing tactical water logistics. Look at systems like the Genesis water cube. They use heavy-duty, armored casing to completely seal off and shield the internal mechanics from that abrasive sand and extreme heat. And to fix the energy problem, they rely on smart hybrid power schemes. They seamlessly switch between solar panels, tactical generators, and battery grids. They're EMP resistant and can pump out over 150 liters a day, completely untethering troops from vulnerable supply chains.
Section 2. The MOF nanotechnology revolution.
But here's the thing. The real breakthrough isn't just shielding mechanical parts with armor, it's a molecular revolution. To actually beat the desert, engineers turn to advanced material science, specifically metal organic frameworks, or MOFs. Engineered at the nanoscale, think of these as incredibly thirsty sponge crystals. Their hyperporous structure acts almost like a chemical magnet, selectively trapping water molecules right out of the dry air, even when humidity drops down to 10%. And the best part? Absolutely no power-hungry refrigeration is required.
Let's watch this engineering blueprint in motion, step by step. Step 1 kicks off at night. Out in the desert, relative humidity naturally bumps up a bit as the temperature drops. The system opens its baffles, letting those hyperporous MOF crystals passively absorb moisture directly from the cool desert air as it flows through. Moving to step 2, watch how the water molecules get securely captured. They are physically pulled deep into the microscopic crystalline voids of the MOF. Notice there is zero active mechanical pumping going on here. It's driven entirely by pure chemical affinity. The MOF is acting as a perfect molecular cage, aggressively hoarding those precious few grams of water from the air. As we hit step 3, the sun comes up. Now that harsh daytime desert sun, the exact same heat that normally destroys standard cooling systems, actually becomes our primary hybrid power source. The system uses this solar thermal energy to passively heat up the MOF desiccant material, kicking off the regeneration cycle. Finally, in step 4, that intense solar heat breaks the molecular bonds holding the trapped water. The MOF releases highly concentrated water vapor into a closed chamber.
Because this vapor is now super concentrated, the dew point gets artificially raised, so the vapor easily and naturally condenses into pure liquid water against the cooler walls of the device. It's a remarkably efficient, completely solar-powered harvest.
Section 3. Purifying the water harvest.
Okay, so we've coaxed water out of thin air, but our job as engineers isn't over yet. Raw atmospheric water is essentially distilled. It's totally devoid of essential minerals and often picks up microdust or dissolved gases like CO2 along the way. So we route it through a strict post-production schematic. First up, active carbon filters strip out the dissolved gases and any leftover dust. Second, ultraviolet light sterilizes the water, neutralizing any airborne bacteria. And crucially, a final module injects essential minerals back in, like calcium and magnesium. This perfectly balances the pH and transforms that raw harvest into healthy, totally safe drinking water.
Section 4. Reversing global desertification.
While military water cubes and single-soldier MOF devices are incredible achievements on their own, our ultimate goal as environmental engineers is much, much bigger: combating global desertification. This timeline outlines the blueprint. We're evolving from today's tactical units to near-term massive solar water farms and smart buildings coated in hydrophilic nanomaterials that basically sweat their own water. Long-term, we're modeling subsurface moisture harvesting and strategic climate engineering to create completely new self-sustaining artificial microclimates. We are literally talking about stopping the spread of deserts.
This brings us to a massive paradigm shift in how we manage global resources. Producing water in the desert is quickly becoming far more valuable than trying to transport it there. By bringing together advanced material science, solar thermodynamics, and heavy-duty engineering, we are rendering vulnerable long-distance pipelines completely obsolete. We now have the tech to generate life-sustaining water directly on-site, literally anywhere on the planet.
Which leaves us with this final thought. If nanotechnology and advanced thermodynamics allow us to successfully mine the driest skies on Earth for water, even at just 10% humidity, how long is it going to be until we can engineer our deserts to bloom once again? Thanks for joining me on this explainer. I really hope it completely changes how you view the empty air around you.